Hi, I'm Ruud. I'm a mathematician, work as a senior staff engineer in the Developer Tools organization at Sun Microsystems. I'd like to welcome you to a 7-module training series brought to you by Sun. It's called An Introduction to Parallel Programming. The trend toward multi-core and parallelization is creating demand for new skills from software developers. In this series, we'll discuss parallel programming as one of the fundamentals of application development. Last time we discussed multi-core chip architectures and the problems they create for developing parallel applications. In Module 3 we will go over parallel architectures and chip memory design. In this module I'd like to talk about parallel architectures. And to start with, I would like to introduce the concept of cache coherence. It's all about the caches. As we've seen in a previous module, the data at the system level, at the memory level, lives in a page, but at the hardware level we move cache lines around. So the data starts in a cache line in memory. That line could be copied into a level 2 cache, say, from there into a level 1 cache. So what I'm trying to show here is that it's very natural to have multiple copies of the same tiny block of data, called a cache line, floating around in my system. In my case, I have 3 copies of identical data. But what if the CPU makes a change to that cache line? If it modifies an element in that cache line. Now I have one different cache line compared to the other two. In other words, I have a cache line inconsistency. And if another core or CPU is interested in my data, I need to make sure it gets the yellow line, not one of the pink copies, because that is stale data. To show you how that works out in a parallel system, I'm going to show you imaginary behavior of a set of cache lines floating around in my system. So my cache line originally starts in memory, and I have 4 CPUs in my little parallel computer, or 4 cores. And let's say CPU 0 needs the pink element. The pink element is part of that cache line, so that core will get a copy of the cache line in its cache. But what if another CPU needs the yellow element? The yellow element happens to be part of the same cache line. So now CPU 2 has another copy of that cache line, and likewise CPU 3 may have the third copy because it's interested in the blue element. So now I have 4 identical copies of the same cache line in my system. But what if one of the CPUs makes a change to the data? Assume CPU 0 modifies an element in its cache line. How do we handle that? The way this is handled is by introducing what is called state bits. The state bits are an extension to the cache line, and they will tell the system what the status is of that line. And like I'm showing here, the red means the line has changed. So certain bits are allocated to that line, and that bit pattern will tell the rest of the system what's going on with that line. So that line is now different. And at the same time, the other copies need to be invalidated, because they have an incorrect version of the pink element, because the pink element is now white. So that's the way to handle these cache line inconsistencies. By looking at the bit pattern, other processors will know that it can no longer use the data, and the hardware will be organized so that it'll get them the right copy of the data from somewhere else. And that mechanism is called cache coherence. So in a cache coherence design, we not only have the data, we also have the state bits. And here I'm showing you an imaginary protocol. For example, I could allocate 3 bits for the status. All 0 could mean the line is clean, that means I can just use it. 001 could mean the line is shared, that means I'm not the only one with a copy. 010 means the line is dirty, means I've modified it. And 100 could mean the line is invalid, that means I can no longer use it. When designing a parallel system with cache coherence, this is part of the work that needs to be done. How many bits are being allocated for the cache coherence? What is the protocol? How does a line change phase, change status? And if you'd like to hear more about that, I would encourage you to look into an architecture manual, because that's where you can find that level of detail. Thanks to cache coherence, we can build shared memory parallel systems. So that's a big plus. So how do I keep track of these changes? And there are different ways of doing that. The fastest way, and in a way easiest, is called Snoopy or broadcast. In broadcast, essentially all devices are monitoring all the address traffic in the system continuously. So at any point in time, they know what's going on. That gives me the lowest latency, so that's good for performance. It gives me very fast cache-to-cache transfer of my lines. So this is really what you'd like to have for performance. The problem is that it's an all-to-all communication problem. Each device will have to monitor all other devices in the system, and that's expensive. It's expensive to do. It's hard to scale to a very large number of cores. So at a certain point, this technology can no longer be used because you're running out of steam. At that point, you could switch to what is called the directory-based cache coherence protocol, or also called SSM, Scalable Shared Memory, which is a point-to-point protocol. In this design, there's a directory. That directory keeps track who has a copy of the line. So once I know who has a copy of the line, I can selectively tackle that cache line in that CPU, and I don't have to bother the other CPUs as they don't have a copy of that line. This allows me to go to much higher bandwidth because I can be more selective in my coherence traffic, and therefore I can go to a larger processor count. In other words, I can build bigger systems this way. But there's a price to pay. The price to pay is that the latency tends to go up somewhat, and it's also no longer uniform. It depends on where cache lines are, as I will explain in the remainder of this talk. It tends to slow down cache-to-cache transfers, and somewhere I have to store that additional directory information. Because in this design, I not only have my data in my cache line, I need my state bits, but I also need to keep track of who has a copy. And on this slide, I'm showing you an imaginary design where I have a bit vector, and that bit vector tells me who has a copy of my line. For example, processor 0 does not have a copy, but processor 1 has a cache line. Processor 2 has a copy of that line as well, and so forth. So 0 means I don't have a copy, 1 means I do have a copy. So now when there's an invalidate, the system will know whom to contact, and therefore also whom not to contact and leave alone. And again, this allows me to go to a higher number of cores or processors in my system. When implementing this, there's a notion of ownership of a line. If you want to build this and make it practically useful, you got to make choices like this. And one of them is to make one cache the owner of that line. That owner plays a critical role if I want to get to that cache line. So if I want to get a copy of that cache line, I first have to talk to the owner. The owner may have handed out additional copies to other caches in the system. The owner takes responsibility. It will return the cache line to me, but maybe it has to check other caches first because it has given out copies of this line. And that will take longer, compared to the situation where the owner is the only one that has a copy of the line and can immediately return it to me. So this creates a non-uniform architecture. The cost of getting to my data depends on where the cache line is and what the status of that line is. And that brings me into a simplified overview of parallel architectures. Simplified in the sense that I will leave out many details, but for the purpose of parallel programming, as we will see in a future module, this is kind of, I think, good enough. The easiest architecture is the good old SMP, which stands for Symmetric Multiprocessor. The word symmetric is chosen because in this design, the memory access time is the same for all CPUs or all cores in the system. So what do we have? We have the bottom of this diagram, we'll see the CPUs with their caches and the memory. The interconnect that connects the CPUs and the caches to the memory system understands cache coherence. What that means is that if I make a change to a cache line, everybody else will know about it. I get global visibility of the changes in my cache lines. That's really what cache coherence does. The architecture of the interconnect could be different things. It could be a simple bus structure, could be a very sophisticated crossbar, or something else. For my purpose, that doesn't matter. Of course, it has an impact on performance and the design. What I like about this architecture is that it behaves like a big PC with more resources. I have more cores, I have more memory. It's easy to use. And it makes good use of the resources because even a single threaded application can access all of the memory, and the memory access time is always the same. This is called a flat memory or uniform memory access design. On the downside, yes, it is more expensive than not putting in cache coherence. But cache coherence gives me so much pleasure that I wouldn't mind paying for it. One thing that I'm not so happy with is sometimes it's being said as being non-scalable, and that's actually a little bit too simple to be true in general. With any architecture you can write a 5-line program to make it or break it. And of course, once you know a design, you can write a program like that. The key thing here is to exploit the architecture as much as you can, and in that way you will get scalable performance. The opposite architecture, and actually that's in a way disappearing from the planet very quickly, is where I have simple nodes, single core nodes. So I have a 1-core node, and it is a self-contained system. It could be a simple PC, laptop, workstation. What we see here is we have a CPU with caches, memory and I/O. Again, think of a simple PC connected through a standard network. The network could be Ethernet, InfiniBand, a specialized network. For the logic, it doesn't matter. The key here is that it does not understand cache coherence. In other words, if I make a change somewhere in my cache, nobody else outside of my own node will know about it, because the interconnect does not propagate the change. And that makes for a very special version of a special architecture of a parallel system. This is called distributed memory, sometimes also called no remote memory access. I cannot access the memory, the other memories in my system, unless I do something special at the software level. And that's why this architecture is also called non-uniform memory architecture. The access time, in contrast with the SMP, the access time depends on where I am. I can access my own local memory very quickly, but if I want to access the memory on another node, I have to cross the interconnect, and that will take time. I not only have to adapt my software to that, but it will cost me time, and that creates a non-uniform architecture. For sure it's cheap. Any office network even qualifies as this kind of architecture. The word scalable here is a little misleading in the sense that it depends on the application. If you have what is called an embarrassingly parallel application that I'm going to explain in the next module, then this architecture will do well. If you have an application that requires more communication, then this architecture may not do so well. It really depends on many factors, as always. Once you have these two basic architectures, you can start mixing and matching, and then we talk about a hybrid architecture. A cluster of SMP or multi-core nodes, for example. I could have each node in my system could be a small or bigger multi-core system or an SMP system. And within that one system, I have full cache coherence and flat memory access. Memory access time is always the same. And then I combine through a regular network like Ethernet or InfiniBand or some other network. The key here is that the second level interconnect does not support cache coherence. And again, what that means is that if I make a change within one node, nobody else will know about it unless I do that through software. And that creates what is called a hybrid architecture, and you get the pros and cons of both. The last architecture I would like to cover is the CCNUMA architecture. Cache coherent, non-uniform memory access. So again, I have nodes. A node could be an SMP system or a multi-core node. Within a node, I have full shared memory. I have a flat memory system within a node. Multiple cores or CPUs, each with their own memory. The difference now is that the second level interconnect does understand cache coherence. That means that any change that I make is propagated throughout the whole system. That gives me the look and feel of a big system, typically with a lot of memory and a lot of cores. But there's a downside. The downside is the non-uniform memory access time. If I'm running somewhere in the system and I need my data could either be in the local memory. If it's in the local memory on my node, it's fast to access. But if I have bad luck, I'm decoupled from my data, my program is running in another node than where my data is, and then I have to cross the interconnect, and that will take longer. And that's not good for parallel performance. So one design aspect when developing a parallel application for this kind of architecture is to make sure that your data is as local as you can to the thread or the core that needs it. Thank you for watching. Please look at the other modules in this series. For more information on how Sun can help you designing parallel applications, please check the URL on the screen or send an email to the email address listed on the screen as well. Thank you very much. We welcome your feedback.